Okay, hi everybody. We're going to look at figuring out what the dimensions would be for an optimal tin can. So, you know, we talked about this in class, how the soup can and the tuna can chose different ratio of dimensions. So we're just going to interpret the question. So we want to know what ratio of dimensions give the largest volume for a specific amount of tin. Okay, so the first thing you should do when you get one of these problems is pick the problem apart and find out what it is you're looking for and then come up with a plan. So the dimensions here would be a radius and a height. Okay, so a radius and a height. Okay, and you can see that the tuna and the soup can both went in different directions with those dimensions. Okay, so largest volume means this is what I'm optimizing. So for the ratio of dimensions, just to go back to that, I'm looking for R to H. Like, are they double? Should they be the same? You know, what would be optimal. And then a specific amount of tin. So if I think about the tin in terms of mathematics, we're looking at surface area. And if I have a specific amount, this is the constraint. Now, in this problem, I don't actually have the specific amount, so we're going to have to just, choose a constant to represent that. All right, so we're optimizing volume, which for a cylinder is pi r squared. So you just take the circle at the top and then stack it the height amount of times. And then surface area, let's call it some amount A, which is a constant. We need to remember that it's a constant when we take the derivative, that A will be treated as a constant because it's a specific amount. Okay, and then if you think about opening a can up, you're going to have two circles and one rectangle. So these are pi r squared. This is H. And then this wrapped around that circle, so it's just circumference. And so then the area of that is 2 pi r h. So this gives us 2 pi r squareds plus 2 pi r h. All right, so now what I want to do is take the derivative of what I'm optimizing, but I need the constraint to be in the optimization problem, and right now it's not. So the easiest thing to solve for is probably H, so that's what I'm going to do. So I get A minus 2 pi r squared equals 2 pi r h, and then I'm going to divide by 2 pi r. Okay, and then I have H is equal to some surface area that is specific, minus 2 pi r squared all over 2 pi r. Okay, and then I'm going to put this into the volume formula. So so this is going to get replaced with this. Okay, so here we go. So the volume, I'll start over here, equals pi r squared times all of this. Okay, and now I can just clean things up a little before I take the derivative. So I've divided by a pi and one of the r's. And then I'm just going to bring that r inside. So I have AR minus 2 pi r cubed. And then everything's over 2. So I'm just going to put a half here. And then this would divide by 2. So let's clean that up one more step. Okay, and now that's going to be nice and easy to take the derivative of. So remember, I'm taking the derivative and I'm going to set it equal to 0. So 0 equals, and I'm taking the derivative with my constant being r, or my variable being r, and a just being, just think of it as like 3 or 4, whatever, it's a constant. So I have a half a minus 3 pi r squared. So I have a half a is equal to 3 pi r squared, and then I could divide by 6. And then I can square root both sides, and I get the square root of a over 6 pi. Okay, so that doesn't really tell us it in terms of h, does it? But a was equal to, if we go back up here, a was equal to 2 pi r squared, you know, the surface area. So we're just going to replace that. So 2 pi r squared plus 2 pi r h all over 6 pi. Okay, and we're going to clean this up. Maybe square both sides might be a good idea. And then I get, and then the 2's are going to, and the pi's are going to cancel. So I have r squared plus rh all over 3. And then I can solve for r. Still tricky here. 3r squared equals r squared plus rh. So I get 2r squared equals rh. And if I divide both sides by r, I get 2r equals h. And so r should equal exactly half of the height. Okay, so the ratio should be a 1. So 1/2 to 1, or a 1 to 2. I could say it 1 to 2. Okay, which if you think about it means that the diameter should be the same as the height. So maybe take a look around in your cupboards, in your kitchen, and your task is to find me that can if it's in your house, and send me a picture of it, and we'll see what we get posted. I'm sorry, my droid is going off here. My text messaging. Okay, so let's see if you can find in your house the optimal can. And I have a guess of what you're going to find, but we'll see. Okay, till next time.